Hi, I'm Ali and I'm a senior developer here at AlphaBOLD. At AlphaBOLD, we take pride in creating intelligent solutions for industrial automation. In industrial supply chain, we see that there are various procedures that require human intervention. While some of these are out of necessity, there are others that are there just because that's how the convention drives, or due to lack of awareness of the existence of a more modern solution that can tackle the problem more efficiently and lead to better results. At AlphaBOLD, we look at these gaps as opportunities to adapt and create more modern, more robust and resilient solutions that lead to more efficient outcomes. Today, we'll be discussing how computer vision can aid to these endeavors. In supply chain mechanism, we have quality assurance, where a batch of production is put to test to see if it upholds the merits of quality. These tests can be of various nature, where it could be a color comparison to see if the batch of production has the same color as that of a desired sample, or it could be the test of measurements, where an object is measured using pneumatic measures to see if length is within the desired range of tolerance. These procedures are more prone to human error and hence can be upgraded by the help of computer vision techniques, where we can use a camera to capture the object of interest and then perform an analysis on the images to provide more quantifiable results. We came across a similar use case with one of our clients, TMG, where the desired use case was to measure the length of a golf club. We used a camera to capture the image of the golf club and then use that image to measure the length. This helped us create a more automated solution, hence removing the possibility of human error. Not just that, it also creates a solution that is more adaptable to be part of an automated solution, hence creating a more seamless transition from one part of production to another.
Alright, so we'll now discuss how this can be completed from a more technical perspective. And the program progresses by taking a couple of inputs from the user or the system that this script can be and will be integrated with. And these inputs are the image that has the object of interest along with the reference object, and the vertical height of that reference object which will be then later utilized to find the pixel to length ratio, and then this pixel to length ratio will be utilized to find the actual dimensions of the object of interest. We start by loading the image into the Python script and converting it from the RGB image that it is to a grayscale image, because that's easier to process. And then we apply a Gaussian blur to this grayscale image, and this essentially smoothens out the image, making it more feasible to apply various computer vision algorithms. With that done, we apply the canny edge detection mechanism to this, and this essentially gives us the edges within the image. These edges are then So now that we have our image with edges inside, what we do is that we make it undergo the process of dilation and erosion. And what this does is that it basically removes the unnecessary edges from the images, the more finer edges from the images. Now that we have more useful edges, we try to find the contours within this image. And these contours are essentially masks that tell us where the object lies within the image and what's the background. Once the background and the objects are separated and we have these contours that are essentially the objects, we try to filter out the noise from these contours. The noise being the contours that are way too small to be actually present within the image. In fact, these are maybe different shades in the backgrounds that the algorithm considered as an individual object. Once these are removed, we take the leftmost object, because that's where the reference object is going to be placed, and we append that in our desired set of contours. And with that, we sort our list of contour and we append the largest object that is going to be the object of interest within that list of contours. So we iterate over these lists, and what we do is we create a bounding box. These bounding boxes are basically rectangles that will be surrounding the contours. Once that is done, we set these contours, these boxes into perspective. That basically sorts them into a clockwise fashion, and we do that. We add different embellishments to make our design more visible, to make our readings more visible, and we calculate. Moving on, we calculate the length to pixel ratio. This is essentially the number of pixels that are there in the reference object, and then that is compared to the length that was provided for that. Well, this gives us that how much length does each pixel represent. And moving onwards, it's pretty simple. We take the object of interest, we count the number of pixels that are there within that object, and we calculate the length. With this being done, we have the length of our desired object. Now let's see how it performs in our experiment with the sample image that we have. And this is how it does. So the object on the left, which is a keychain, has a length of 3.238 inches, which was measured using a vernier caliper. This was the reference object. And the object on the right, which is essentially a fountain pen, that's basically the object of interest. And once the results did come out, we were able to compare them using the vernier caliper, and it was quite promising. So this is how it can be implemented in various other technologies, various other manufacturing processes, and can lead to much better and more streamlined results.